Welcome to reaction mechanisms. So, most chemical reactions occur by some series of steps called the reaction mechanism. So the mechanism tells us exactly how the reaction occurs. So you may be familiar with the Calvin cycle from biology. So energy from sunlight comes in, there are some chemical reactions that occur, and we get glucose out, or we don't as humans, but plants do, things with chlorophyll, get energy from the sun. So let's consider the reaction between nitrogen dioxide and carbon monoxide. So we have NO2 plus CO, react to give us NO plus CO2. So this is a simpler reaction mechanism than the Calvin cycle is. So let's look at this one instead. So experimentally, we can determine that the rate law looks like this. So we have the rate is equal to K, or rate constant K, times the concentration of NO2 squared. And note that now we have a second order reaction in NO2, and we don't have CO in this rate. Now, if we write the concentration of CO, carbon monoxide, but we haven't shown it, that means what we really have there is a zeroth power up here. Because anything to the zeroth power is 1, and when we multiply 1 times anything else, we're not changing that other number. So we now have a reaction. We know that our reaction is second order with respect to NO2, and it's zeroth order with respect to CO. So note that now our rate doesn't depend on how much CO we have around. As long as we have some CO around, the reaction proceeds. When we run out of CO, then the reaction stops. So in this case, the reaction mechanism looks like this. We have one NO2 molecule reacting with a second NO2 molecule to form NO3 plus NO. And this occurs with at some rate constant K1. And then we have our NO3 reacts with our CO to give us NO2 and CO2. So note here that we're using up 2 NO2 molecules, but we're producing 1 again. And in doing so, we're producing NO3 that we then decompose in the next reaction. And so overall, we're producing our NO and CO2, and overall, we're using up 1 NO2. The other one is being created again, being remade, and we're using up a CO. So again here, this K1 and K2 are the rate constants of the individual steps of a reaction, right? So this is our first step with our rate constant K1, and this is our second step with rate constant K2. So again, I've written those here. So NO3 is an intermediate. An intermediate is a species that is neither a reactant nor a product, but it's formed and then later consumed during our reaction sequence. Right? We form it here and we consume it there. So it's an intermediate because initially, at the beginning of the reaction, it's not around, and at the end of the reaction, it's not around. It's only around for a short time in between. But it may be around in significant quantities. It may take a while to go away. It may, if the top reaction occurs quickly, then we'll make some of this, and if the bottom reaction occurs slower than the top reaction goes, then we'll have some of this NO3 around. We'll have a significant concentration of it around. If the second reaction is really fast compared to the first, then every time we make an NO3, almost immediately it will get decomposed in the second reaction again. And so our concentration of NO3 will never get very high. But again, our intermediate is only around temporarily. So each of these steps that I have up here are called an elementary step. So an elementary step is a reaction whose rate law can be written from its molecularity. And this basically means it's an elementary step. It can't get any simpler. We can't break that step down into some combination of smaller steps. Which means what we have to have happen for this top step to occur is we have an NO2 molecule has to collide with another NO2 molecule. If those two NO2 molecules never collide with one another, the reaction never happens. And likewise, at the bottom step, we have to have our NO3 intermediate reacting with our CO in order for the reaction to occur. So, the molecularity is the number of species that must collide to produce the reaction. So, a unimolecular reaction is a reaction that involves only one molecule. Now, I don't mean only one species. Like in the last slide where we had an NO2 reacting with another NO2. In that case, we have two molecules reacting, so that's not a unimolecular elementary step. That would be a bimolecular elementary step. So a bimolecular step is a reaction only involving two molecules, and a termolecular elementary step is a reaction involving three molecules. So termolecular reactions are fairly rare because having three molecules collide simultaneously is statistically unlikely. So having one molecule collide, it doesn't have to hit anything, it's always by itself. So a unimolecular reaction isn't uncommon at all, because all we need is one molecule, it may just spontaneously decompose into something. With a bimolecular step, we have to have two molecules strike each other. That's not terribly uncommon. Molecules are moving fairly quickly at normal room temperature, and this means that quite often we will have our two molecules striking each other. Now, they need to be hitting each other in the right orientations for the reaction to proceed, so it's not like every time they hit each other they react. But with a termolecular reaction, we have to have two molecules coming together at exactly the same time, and the instant that they collide, we have to have a third molecule hit them as well, which is pretty darn unlikely, because the molecules are colliding only for just a tiny, tiny fraction of time. And this means that having all three molecules come together in the right orientation and at exactly the right time is pretty darn unlikely. And we don't even talk about an elementary step that has a molecularity of 4, because that would be that in addition to having three molecules collide at exactly the same time, now we have to have another one come in at exactly the same time too. It just gets more and more unlikely the more molecules you put together. Now, a way to think about this is like driving a car. If I put my daughter behind the wheel of a car, that's like a unimolecular reaction, right? My daughter is probably going to crash that car really, really fast, right? She doesn't need anybody else on the roads to get it into an accident. Now me, I'm a significantly better driver than my daughter is, and so note that my daughter is 3.5. I'm not trying to disparage my daughter. She's not able to drive a car. I can drive a car, so me getting into an accident probably involves me and some other driver, but getting two cars to hit each other is less likely, but still not impossible. I've been in accidents before. But a termolecular accident, an accident involving three cars that all hit each other at exactly the same time, is pretty unlikely. Right? I'm not talking about two cars hitting each other and then later a third car coming in. I'm talking about three cars all striking each other at exactly the same time. Right? That's pretty unlikely. Right? It happens all the time on a highway where you have one car rear-end another, and then the next car later then comes in and strikes the two that are now stopped. But that's not the sort of thing that we're talking about. For our reaction to occur, we need to have all three hit at exactly the same time. I've never seen an accident that involved three cars that all struck each other simultaneously. And then, of course, 4 would get even more unlikely, and so on. So, we can now write the rate laws for each of our elementary steps. So, with step 1, again, looked like this. We had our NO2 plus NO2 reacting to give us NO3 plus NO. Remember, NO3 was our intermediate. NO is one of our products. And so now, if we know that this is an elementary step, only if we know this is an elementary step, then we can write the rate law. Right? We do, in fact, know that this is an elementary step, so now we can write the rate law. We can say that the rate for this step, I'm noting that this is step 1, so it's rate 1, is equal to K1, that's the rate constant for our reaction, times the concentration of NO2, times the concentration of NO2. So we're taking our first reactant and plugging it in here, taking our second reactant and plugging it in there. Now, it's the same species, which means that we get a result of K1 times the concentration of NO2 squared. And this is why it's a second order reaction. So for our second step, for step 2, we again have our intermediate NO3 reacting with carbon monoxide, CO, with our rate constant K2 to give us our NO2 and CO2, carbon dioxide. So there we have rate 2 is equal to K2 times concentration of NO3 times the concentration of CO. So a reaction mechanism has to satisfy 2 requirements. The sum of the elementary steps must give the overall balanced equation for the reaction. That sort of makes sense. In order for our mechanism to be a valid mechanism, we have to start out with the reactants and end up with the products. We can't be making something extra. We can't be destroying something. Now we can make and destroy something in between. We can form an intermediate and then destroy it later on in the mechanism. But we have to have the same overall reaction as what we actually observe. So the second condition is that the mechanism must agree with the experimentally determined rate law. I'm only going to get into this a little bit, but let's check that the sum of the elementary steps for our mechanism gives the overall balanced equation for our reaction. So we have NO2 plus NO yielding our intermediate NO3 plus NO. And NO3 plus CO react to give us NO2 plus CO2. And that means when we add them together, we get this top line. And of course, you notice that we have 2 NO2s there. We have our NO3 here, but we're also producing an NO3, so let's cancel those out. We're also producing an NO2 and using up an NO2, so let's cancel those. And now we have, after we've simplified, we get rid of the things that I've crossed out, and we end up with our overall balanced reaction that we started with. So that first condition we've met. So now let's check whether our mechanism matches the experimentally determined rate law. So remember, the experimentally determined rate law looked like this. Rate is equal to K times concentration of NO2 squared. And remember that our rate laws for steps 1 and 2 look like this. We have rate 1 is equal to K1 times concentration of NO2 squared, and rate 2 is equal to K2 times concentration of NO3 times concentration of CO. Well, you've probably noticed that our experimentally determined rate law matches the rate law for our first step. And this means that our first step is the slow step. This one is occurring slow. That first step occurs slow. Once that first step occurs, the second step occurs relatively quickly. And so it doesn't matter what that rate of the second step is. The second step is being limited by how fast the first step occurs. Because that second step requires us to have our intermediate, that NO3, around. And as soon as it is around, then that second step goes to completion. And we've destroyed our NO3 again. So the rate for our overall reaction depends on that first step. So in any mechanism, one of our 2 steps occurs more slowly than the others. And this slowest step is called the rate determining step or the rate limiting step. Because if it's occurring more slowly than all of the other steps, then the overall rate is determined by the rate of this slow step. So imagine in a factory, you have a bunch of workers and they're all doing one small action to manufacture some product. Who's ever going the slowest, that's going to determine the overall speed with which you can produce your products. If 9 of the 10 workers that you have are taking 1 minute to complete their step, and your last worker takes 10 minutes to complete his step, you can't produce anything faster than 1 product every 10 minutes. Everyone else is going to either build up a stockpile of things that they're finished with, or they're going to be sitting around for 9 minutes waiting until their colleague has finished, and then they'll right away finish their their step and hand their product onto the next person in line. So there's going to be somebody that's moving slower. Just like that, in a mechanism, there's some step that's occurring slower than all the other steps. That's our rate determining step. So since the experimentally determined rate law matches the rate law for step 1, this means that step 1 has to be our rate determining step or our rate limiting step. So that was reaction mechanisms.